Today's lesson is going to be about the electric field. This is an extension of what we've already learned about electric force. In today's lecture, we're going to learn how to draw electric fields and calculate the electric fields. Okay, so first off, let's talk about the field forces. Okay, there are three primary field forces. We've already learned about gravity, and we're learning about electricity. There's a third one for magnetism, but we're not really going to focus on that this year. Okay, all of the field forces basically work at a distance. There's no contact required. Okay, so the fact that the moon is orbiting the Earth, that's because of gravity. Okay, but there's no connection between them really. Okay, so, and because we have this non-contact, it's often helpful to imagine what the force would be on an object at a certain point. And that's where the gravitational field, or in this case, the electric field, comes in. Okay, because close to the Earth, okay, the gravitational field or force due to gravity always points down at 9.8 newtons per kilogram. Okay, far from the Earth, the gravitational field, we are aware, points towards the center of the Earth because gravity attracts everything. Okay, and so a couple of things about fields. Okay, the first thing you need to know is that fields are vectors. Okay, you see the arrows, and that reminds us that they have both direction and magnitude. And for both gravity and electricity, the magnitude of that vector gets smaller as distance increases by r squared. So the electric field represented by E and the gravitational field represented by G, both are proportional to 1 over r squared. And the field vector indicates the relative force that a mass or a charge would experience. So if I have more mass, I have more force. Okay, and if I have more charge, I also have more force. Okay, so that brings us to drawing the electric field. Okay, the electric field is by definition is the force that a positive charge would experience. So we draw the field going away from a positive charge and going towards a negative charge. Okay, and that's something that you pretty much just have to memorize. Okay, so remember, it goes away from the positive and towards the negative. Okay, at times, okay, a mnemonic that I've used, okay, in the past for remembering this is that the positive charge kind of looks like a bow and arrow. Okay, so from the positive charge, bow and arrows shoot arrows, and so the arrow goes away from the plus sign. The minus charge, however, on the other hand, kind of looks like a dead person. Okay, and the person's dead because it was shot by the arrows. So that's one way that it's a silly mnemonic, but if it works, great. Okay, the arrow goes away from the positive and towards the negative. Okay, so as we can see, the electric field from the positive charge goes away, and the electric field goes towards the negative. That gives us the direction of the electric field. Sorry, okay, but the magnitude of the electric field is something that we'll have to calculate, and we've already gotten halfway there when we calculated the force. Because the force is given by kq over r squared, and by definition, the relative force then is that force divided by the little q. So I'm basically just left with kq over r squared, where the big capital Q is the charge responsible for creating the electric field. However, the electric field can also be calculated if I just stick a 1 in for little q. Okay, and so in drawing the electric field fills the entire space. These pictures are way overdone. We're never going to need that many. In general, I would only need about 6 vector arrows for me to get a sense that you know what's going on. Okay, and these field vectors pretty much only show direction. Magnitude is something very difficult to show, and we'll calculate that separately. But direction alone is an important aspect. Okay, and so when we draw field lines, okay, Okay, there it is. Okay, we must remember primarily that field lines will never cross each other. Okay, because if I had two field lines crossing each other, right there at the center, okay, remember the field lines represent the force on a charge if I place the charge at that point. So where those field lines cross, imagine if I put a charge there. That charge would experience a force in two different directions, which is an impossibility. Okay, and so that's why we can never have field lines crossing each other. That's going to be true even when I have multiple charges. Okay, so here I have two equally large positive charges. And the field lines for these positive charges go towards each other, goes away from each charge, and on the sides, yeah, it looks kind of like, like you would expect. But in the middle, it has this thing where they get closer and closer to each other, and then they realize, oh no, I can't cross. And so they just swerve and go away from each other. Okay, so this is the view for two positive charges in the electric field from two positive charges. Okay, one suggestion I have given to people in the past is that these are two positive charges. They're repulsive. The force between them is repulsive. And the way these images look to me, they kind of look like smushed spiders. Okay, and there's very little in my mind that's more repulsive than a smushed spider. Okay. In another situation, we can have one positive and one minus charge. Okay. If these were two minus charges, the arrows would just simply be on the other end of these lines, pointing towards the charges. Okay. But when I have a plus and a minus, this is a situation where the force is attractive. And so the field lines still go away from the positive and towards the negative. And you can kind of imagine if these things continued on, that these things would continue circling back and around, and then this would also go all the way out and then back in here. Okay, and so this is a situation where I have a positive and a negative charge, and the force here is attractive. And this kind of picture always reminds me of mitosis, with cell division. Okay, I believe it's telophase, but don't quote me on that. Okay, and so now we get to the concept of net electric field. Okay, this is exactly similar to what we've talked about for net electric force. Okay, where we take the individual forces from the charge pairs, okay, and add those up. With electric field, I don't have a pair. I only have one charge at a time. That's one of the differences between electric force and electric field. Okay, and so I take these charges and I add them one at a time, the electric fields from each charge, and I add them all up graphically. Okay, because they're vectors. Okay, so if it's two-dimensional, I have to worry about I hat, j hats. If it's one-dimensional, I have to worry about one of those, okay? Or if graphically, I can just tip to tail them. So an example of this would be our common number line problem, okay? So we've seen this and we have many of the same aspects, okay? The first one is to draw the the point that I'm looking for. I'm looking for the electric field at the origin, which would be this point here. Okay, so I just find that point and place an X at that point. That's similar to our draw the picture step. Okay, steps 2 and 3 are similar. I have them switched here from the way I did it for force, but we can switch them back. Okay, step 2 would be to calculate the magnitude from each charge. Charge 1 to the origin, charge 2 to the origin, charge 3 to the origin. Okay, so the distances and the charges will be different. Okay, step 3 would be to draw the direction of the electric field from each charge. Okay, and so to draw the electric field, we simply need to remember positive away, negative towards. Okay, so all of these charges are positive. So charge 1, to go away from charge 1 is this way. Okay, away from charge 1. Similarly, Charge 2 to go away from charge 2, if I'm at the origin away from charge 2, is also to the right. Charge 3 is positive and I need to go away from charge 3. Well, away from charge 3 is this direction, okay, to the left. And again, we're going to be using these arrows to determine whether I'm going to put a plus sign in front of that electric field or a minus sign in front of that electric field magnitude. Okay, so this would be plus E1. E at the origin is going to be plus E1 plus E2 plus minus E3. Okay, and so that's similar to what we did for force. Okay, and at the end, okay, the resulting sign, as expected, will indicate the direction of the net electric field. Okay, in this picture, as long as 3 is not much bigger than 1 and 2, it will likely point to the right. Okay, so moving on, okay, we use an electric field, a uniform electric field, similarly to the uniform gravitational field that we use for Earth. I can create the uniform electric field by having a plus sign and a minus charge. Two parallel plates, one positively charged and the other one negatively charged. And the electric field goes away from the positive towards the negative. And everywhere in this region, okay, the direction and magnitude of the electric field is going to be the same. Okay, we'll talk about how to calculate that at some later point in time. Okay, but at least at this point, this parallel charged plate situation is what we call a capacitor. Okay, and so a capacitor is a way that we can store electrical energy. And if you think of these electric field lines kind of as rubber bands, okay, as I move the two plates closer together, like letting the rubber bands relax a little, or if I pull them apart, that's a way that I can store energy, or I can put more rubber bands because I can put more charge on my plates. Okay, and I'll use that energy at some later point in time to move my electrons around my circuit. Okay, so like I said, this is basically nothing more than a capacitor. We only very briefly touch on capacitors this year. Next year in IB Physics, we'll look at these in much more detail. Okay, thank you.